Sir, we are live now. You can start.
Okay. Yeah, so how are the questions going to come? Is it on the chat box or?
Yes, sir. Just like last time, you have to see the YouTube link, the live chats there.
Okay. So, Achintya, have you opened the YouTube link?
Yeah, I have opened the YouTube link. We'll reopen it once more. Yeah. Okay, so there were two questions which were already there in the forum. Maybe we can take them first.
Mm-hmm.
Okay. The first question Sarthak is asking that in lecture 45, uh, basically he's asking that you are telling that H naught is actually a sum of flock operator in the case of many-body perturbation theory. And from the non-interacting theorem, we know if I can write the Hamiltonian as a sum, then I can write the wave function as a product. His question is that in case of Hadrey-Fock wave function, that's a stator determinant. So that's not as only product, but it's a determinant. So how this non-interacting theorem is applicable?
Yeah, I'm not able to hear because here I think two devices. There's some echo coming.
There's an echo coming. Just give me a second. What about now?
No, better.
Yeah.
Try.
So his question is that in the case of many-body perturbation theory, you have told that H naught can be the summation of the Fock operators. And Sarthak has a question that, of course, it's true for a non-interacting Hamiltonian where you can separate out the Hamiltonian additively. The wave function will be a product. So his question is that in the case of Hadrey-Fock wave function, it's a determinant, not a simple product. So he's asking that how the non-interacting Hamiltonian's behavior can be written as product in this case. Dr. Pal, am I audible?
I'm sorry, there is still a lot of problem.
There's a noise coming up.
Two devices going on, one after another. When you are talking, then something else going in the background.
Okay, I understand.
I am not able to understand at all. Maybe if you see, if you see, you can try to answer the question, then I can.
Can you hear? Can you still hear the echo now? Can you hear me?
Yeah, I have switched off everything now.
Okay, can you hear me now?
Yeah.
Is there any noise anymore?
No. Now it's okay.
Okay. So what Sarthak is asking...
I understood the question. The H naught is sum of the Fock operator. Then what is the question we just did?
So he is asking that in case of Hadrey-Fock wave function, it's not a normal product but a full determinant.
Yeah.
So he is asking that how the non-interacting Hamiltonian can be used in this case. How the eigenvalues will be still the sum of the eigenvalues of the Fock operator.
Oh, that is simple. Because in determinant, there are n factorial terms. Each of them is an eigenfunction of H naught. Right? You have, let's say, chi1, chi2, chi3 to chi-n. In some order, they will come. Each of those n factorial product is an eigenfunction of the H naught. So, sum of their n products will also be eigenfunction. And their eigenvalues are the same, which are basically sum of the orbital energies. So it does not matter whether it is chi A1, let's take a two particle system, chi A1, chi B2 minus chi B1, chi A2. For each of these two terms, the orbital energy is EA plus EB. So these, for the n factorial terms, it's like degenerate orbitals. So if I just sum that the eigenvalue will still remain EA plus EB, multiplied by chi A1, chi B2 minus chi B1, chi A2 with 1 by square root 2 factorial, whatever. So the determinant still remains the eigenfunction, and the eigenvalue still remains what would have been the eigenvalue for only one term, because they are all same. So as you know, if there are two eigenfunctions with the same eigenvalue, if I take a linear combination, the eigenvalue does not change. So that is the reason the eigenvalue remains the sum of the orbital energies. So Achintya, if you want to explain any further.
So I think the straightforward, easy way, what's I told, is to do it by take a 2 electron case. You write the determinant, you'll be straightforwardly able to see. And remember, the normalization constant also play a role here, because it will make sure that it still remains the sum of the eigenvalues.
Yeah, so the important thing is that determinant has n factorial terms, I agree. So that is where the confusion is. But each of the n factorial terms is an eigenfunction with the same eigenvalue. So if you take a linear combination, that is very easy to show, the eigenvalue will remain the same. The wave function will become combination, and that is what is happening. The wave function is becoming a determinate, but the eigenvalue is simply sum of the orbital energies.
Another question. So this question, the next question is much more specific. So he says that he asked a question about the software Orca, where he says that the software prints start incremental Fock matrix formation. He wants to know that if the exact Fock matrix, how it is formed, can be seen from the program. And so I will answer this question.
Yeah, you can answer. It's an iterative method, so you can answer the question.
Yeah. So basically, I don't think there is any keyword which can print out the exact Fock matrix. That's what I was trying to search. But I believe there is no keyword which can actually print it, the Fock matrix at each step. But you can use some other software, like you can use a Gaussian or a GAINS US, where you can actually print out the Fock matrix at each step and see how it's changing at every step. Maybe we will put some online output file in the forum so that you can see how the output file looks at its changes at each step. Now, the next question is about what is convergence acceleration in Fock in the SCF calculation.
Yeah. So normally the density matrix, that is a charge density bond order matrix, is computed at every iteration. As you know, that is for the RHF case, it is 2 times CC dagger. C is the coefficient matrix. And then at every iteration, because C's are changing, the charge density bond order matrix will change. So you put some value on the charge density bond order matrix changes. So you take them, square of them, so that it becomes positive, the difference square for n to n plus 1 iteration, and ensure that difference is less than a preset value, which can be as tight as the computer time that you want to spend, typically 10 to the minus 7, minus 8, something like that, which is good enough. So that is basically the charge density bond order matrix at the nth iteration and n plus 1th iteration. Sum over all the elements, P mu nu, sum over all the elements, square that difference and sum over all the mu nu. So that becomes a positive quantity, and then you make a kind of convergence of that. And that convergence, sometimes most of the programs, I don't know again in Orca, most of the programs you can change that convergence. It's up to you. You can give in the input.
Yes. So he also asked this question about the DIIS method of interpolation.
Yeah. So DIIS method, I say normally when you do an iteration, we take the last iteration value, we start from the last iteration value and then do the iteration. So basically at the nth iteration value is taken in the n plus 1 starting value. But in DIS, initially you do that, but you generate a few subspace, let's say 5, 6, 10. After that, let's say you have a 10 subspace, then 11th one is a linear combination of all the 10 coefficients. In this case, coefficients are changing, all these coefficients. So that is called direct inversion on an iterative subspace. So those coefficient, linear combination coefficients can be obtained by an iteration, by a direct inversion on that 10 subspace. So usually, typically people take 5 or 10 subspace to start with. That accelerates the convergence. So basically, I don't take the last value as the current value, but maybe I build 5 or 6 subspace. Then after that, the last 5 subspace combination as the next value, next current value. So that if you have an oscillation, it works very well, particularly when there is oscillation. The last value, it brings it down, then again it goes up, brings it down. So if you take the average, the combination gives an average, then you come down to the converged value quickly. So that is the philosophy of the DIS, and that is very successfully done. In fact, many people have got very accelerated convergence by simply using DIS method. Yeah, Achintya, if you want to clarify more, you can do.
Yeah. So basically, if I want to clarify in a much more easier way, so like if I seat my hand like this one, like from the hill and coming down to the valley. So if I take my step, if I just take the last step's value, then what can happen is that I can overshoot the valley and go to the other hill. So that essentially means that I will not hit the valley at it. But if I am taking the guess from last 5, 6 steps, so I know that when I am reaching the valley, I have to now remove the step size, so I have to walk more slowly so that I exactly hit the valley and actually reach to the convergence. I think Sarthak asked further to this question, what do you mean by subspace in the case of convergence acceleration?
Yeah, so subspace is, as I said, I am not I can have 100 iterations, but I am not taking all the 100 iterations space. I take a small number of subspace, 5 or 10 iterations, then take a linear combination in that subspace to start the next iteration. It is called subspace because the entire space is a larger number of iterations till it converges. But before that, we take a subspace combination to restart the calculation so that it becomes much faster. So as he said, if there is an average, actually is an average of these two, you are missing all the time because they are going up and down. So if you take a combination of a few set of iterative values, you will go to that particular converged value very quickly. So because all it depends on the guess. Because if this is the converged value, if your guess is here and the next result is here, then the next one again going up, then you are missing this. So if you take a linear combination or simply an average, then you will be coming here and then it will quickly converge. So that is the whole idea. So subspace, it is called subspace because the entire number of iterations are not taken. So in a smaller subspace, I am building this.
I hope this is clear. So these are the two questions we had unanswered in the forum. So students can ask if they have any other questions.
Yeah, the SCF, I just want to tell the student, SCF convergence is a very tricky thing. So you have to use as many options as possible. So DIS is only one option. The guess itself, the initial guess itself is an option. So many people take a guess of the extended Hugel calculation. So, or maybe if you have some idea of the density matrix, from there you can take the guess, maybe from experiment, whatever, some idea. So the guess is one very important option. The second is this DIS, if you want to build the DIS within a small subspace. Then you have to damp it, sometimes you damp it. The results are going too high, so you damp it. And the damping is usually done by several approximations. One of them is per day approximation. So there are several tricks of trying to converge. But as long as you can say that how do I trust the result? As long as it converges, the results can be trusted. With converges means starting with the last iteration, I get the next iteration as the same as the last iteration, or nearly the same within that approximation, within my delta of the density matrix differences. Then I can trust it. But how I approach it can be anything. So there are so many strategies of approaching. The standard thing is you don't do anything, just make a guess and then let the SCF iterations run. But if it does not converge, then you have to do many of these tricks. And if you don't do, then sometimes you get wrong results. In fact, you can also converge and get an excited state convergence. That's what I was coming directly, then you get ground state. So, because Hartree fog is a nonlinear process, there is no guarantee. And so unless you, in fact, it's a smart idea sometimes to try in 2-3 different ways, and you see if the same convergence comes. If you want to have more confidence. So SCF convergence can be tricky, and if you are not very sure that it is converged correctly, you will continue to do your correlation calculation and say wrong. You are starting from a different state, different Hartree fog itself. So, and I can tell you, many people who are working on the computation, they do not pay enough attention to the SCF iteration. Sometimes I have seen people don't even see that it is not converged. Still they go ahead with the correlation calculation. So, and even if it is converged, has it converged to the right state? Sometimes it converges, but converges very, very slowly. So if you have given 100 iteration bar, it is almost there, but it is still not there. So it has not yet converged, which is okay, because at least it has converged to a reasonably good extent, as long as it is not oscillating. Oscillation, then you don't know where you are. But if it is monotonically converging, but it is slow, then it is still okay, because you are on the right track. Then you can come to your desired convergence by certain tricks, by which you can accelerate this convergence. So these are some of the things that you must learn, because SCF is SCF iteration, SCF itself is more complex than even CI. CI is very simple. It's a linear expansion in a basis shape. SCF has a physics of mean field theory. It's a nonlinear thing. So it is much more complex than CI, at least CI as a correlative. That is simpler to understand it. So I would say that, and SCF is the starting point of all correlation calculation. So people must pay attention to the Hartree fog. And that is same as if you do DFT, incidentally. So DFT, as I told last time, is basically very similar to Hartree fog, but the matrix of the operator is different. So the elements are a little bit different in the sense that you have exchange which is not exact, and you have some parts which are correlation. So because of the exchange correlation part coming in, it's different, but it is basically, as far as the convergence is concerned, the Kohn-Sham convergence is also very similar problem. Similar problems and similar strategies can be used in the DFT convergence also.
I just want to add that because modern day many of the quantum chemistry software packages are so smart that they even don't throw an error message if the SCF has not converged. So one need to be really careful to check it.
Oh, and that is very dangerous.
And what Dr. Pant told is something very interesting, is that sometimes the excited SCF can converge to an excited state. And if you are not careful enough, if you do not use your chemistry sense, it's very difficult to understand that it has converged to a ground state or an excited state. So one of the easy hack is you can do an excitation energy calculation on that SCF state. If your SCF has converged to an excited state, the moment you do an excitation of the top of it, now it will fall back to the ground state. So you can see negative excitation energies. And that's one of the classic way to understand that your SCF has converged to an excited state. But it may not be a problem in many cases. In many cases, you want to convert your SCF to an excited state. Suppose you are interested in a core excited state. you may like to convert your SCF to an excited state so that you can get idea about how the core excited state energies looks like. So software is allowed to do this kind of calculations.
A simple problem that can also happen if you don't converse properly is what is called symmetry broken solution.
Yes.
So for example, if you're doing a nitrogen calculation, you should get pi orbitals. So pi orbitals have to be doubly degenerate, but you will see that the orbitals are not exactly same energy, ground state nitrogen, Hartree Fock. That means your Hartree Fock is wrong. It's a symmetry broken solution, and you will get completely symmetry will be lost and results will not be correct. So you should check. I would request all of you to check the Hartree Fock orbitals if the symmetry is preserved before you go ahead. Because simple Hartree Fock orbital symmetries are what you are taught in hemodiagram, normal hemodiagram, which are basically one particle diagram, like dinitrogen, as I told you. Hemodiagram is basically Hartree Fock diagram. So if you don't reproduce that energies exactly, then there is something wrong. If you are converged, then almost 8, 9, 10, 11, 12 digit orbital energies will be identical for pi. Okay. So I think you should see that the degeneracy is correct. If it is not, then there is a symmetry broken solution. How bad it is, that depends on where it is broken. If the difference of the two pi orbitals in the third digit is pretty bad, because they are all in Hartree unit. So if it is in 10 digit, maybe you can still survive, but ideally it should not happen. So you should be able to go back and check the convergence properly. So I think these are very finer things that one must check if you really, otherwise of course you just leave it to the software and you never know what happens, because depending on the basis set, unfortunately, depending on the basis set also the convergence changes. So what will converge in, let's say, STO3G may not converge in another basis. So that is a dangerous, that is what it is more dangerous, because the matrix is of different size. So as you go, the convergence may get lost in one basis and not in another basis. So that is why you have to be even more careful that every single output you should check properly. And in fact, it's very instructive to read the output of the SCF. You will see every small thing, charge density, bond order matrix, how they are changing at every iteration. So proper reading. Unfortunately, as Achintya was telling him, so many software don't print everything these days. But those who want to learn, I think print is a good option. I'm sure there will be an option of printing. And that print option essentially means that the output will be larger. But for small molecules, it's very instructive to look at the output and learn from the output, very small details.
I don't see any further questions. So if you have further question, please go ahead and ask. Okay, Sarthak has another question. What is called an SOSCA for a second order SCF?
What is it?
What is a second order SCF?
We don't teach that, but you want to answer it?
Yeah, so basically when you are calculating when you are minimizing the energies with respect to the orbitals, generally we know that to find out the minima, you actually need the information about gradient. The gradient has to be zero. But if you just have information about gradient, that information is not sufficient sometimes to get convergence. So you need to calculate also the Hessian of the orbitals, that is the second derivative of the orbital matrix. And that's why, and that can help you convergence in difficult cases, where especially for transition metals, where many of the orbitals are near degenerate, that time SCF convergence can be really difficult. For that, you have to switch to the second order SCF, or what is called an SOSCF. But they are of course more expensive because you have to calculate the orbital Hessians, but you cannot avoid it unless the convergence thing is there. So some of the software packages, they give you the option that it's automatically can switch over to second order SCF if the normal SCF fails to converge. Second order SCF is a more robust technique to achieve convergence in the case of difficult convergence cases. other question here, then maybe we can close the session.
Yeah.
Anyway, if there is a further question, always put on the.
Oh, yeah, we will have more interaction session, of course, after maybe a couple of weeks or so. So we'll have more interaction sessions. You can again ask the questions if you missed something here.
Sure. Yeah. Okay, so we can close it here.
Yeah. Thank you. Thank you all.